I am Amitpal Singh, and together with my partner Lay Patel, we are going to give presentation on our 998 project. And the title of the project is Frequency Control and Load Flow Analysis of Grid comprising conventional, renewable energy source and electric vehicles of remote community of Ramea Island of Newfoundland. Ramea is a very small island in Newfoundland and has a population of slightly less than 400, that is around 388. The primary source of power in Ramea is diesel generator sets. There are a total installed capacity of 2775 kilowatt of diesel generator sets. Apart from this conventional energy source, there are also some wind turbines. There are 6 into 65 kilowatt wind turbines provided to the community by Frontier Systems. And the installed capacity for these wind turbines is around 390 kilowatts, and there are three turbines of 100 kilowatt totaling 300 kilowatt which were supplied by NL Hydro. Uh, Besides this generation, the total load profile on Ramea Island is 428 kilowatts. So the microgrid at Ramea Island consists of diesel plants along with wind turbines. The wind turbines also generate a significant amount of surplus energy. So earlier it was envisaged that this surplus energy will be used to generate hydrogen using 162 kilowatt electrolyzers, and that hydrogen will be burned in an internal combustion engine to generate electricity during peak power demand time. However, there are certain issues going on with the internal combustion engine, and as a result, this system is currently not functional. The paper proposes the following three options of renewable energy sources. The first option is a 150 kilowatt wave energy generator, which generates electricity using wave energy from the ocean. The option two is 150 kilowatt pump hydro generators, in which the seawater will be pumped upstream in a reservoir during surplus generation, and whenever load demand is there, and the stored water can be used to generate electricity. In the third options, collectively, when electric vehicles are connected together to the microgrid, they can act as energy source. So the third option consists of using electric vehicles battery as a collective energy source. So with our proposed system and with the existing system, what is the need for frequency control study? So we see that whenever there is a large renewable energy penetration, the microgrids can become unstable. Although there is an advantage of a reduction in emission, however, some sort of instability can be created, for which various studies are required. Wind and solar power are non-synchronous generators, so their governors do not have that significant capacity to control the frequency. Frequency in a microgrid or in any grid is actually given by the balance between the active power generation by the generators and the active power consumed by the load. So whenever there is a exact balance between the active power generation by the various generators, and the active power consumed by the loads, the frequency will be constant. And whenever there is a increase in demand in the load and the generation active power is less, then the frequency will drop. And similarly for the increase of frequency when the load is reduced. The same phenomena goes for the voltage also, but in that case, the change in the reactive power demand of the load will decide the voltage of the microgrid. So whenever a new renewable energy system is connected to an existing renewable as well as conventional energy generation system, as in the case of Ramea, we need to carry out certain studies. So whenever a new generation is being added to an existing generation, then we need to see how the load will be distributed among the older conventional diesel generators and the wind turbines, and the new proposed system like the hydropower plant. As a result, we need to carry out what is called as the load flow studies. In the load flow study, we are able to calculate what will be the various active and reactive power flows from the various sources under different scenarios, and also what will be the voltage drops at various passes. By adding more and more renewable to the system, we can make the microgrid unstable, especially with regards to frequency and voltage. So the equilibrium or balance of frequency exists when the active power generation by the generators matches with the active power consumed by the load. Similarly, the voltage remains stable when the reactive power generated by the generator matches with the reactive power consumed by the loads. As a result, an equilibrium is essential for having stability with regards to the active power, with regards to the reactive power, as well as during the voltage drops. Now, when we add more and more sources like hydropower, wind turbine to the loads or to the microgrid, then this will also increase the short circuit ratings at the various passes. So there is a need to carry the short circuit studies also. So these short circuit studies will give us the various fault levels at the various passes in the microgrid. And to ensure safety, we need to see that these fault levels which are obtained through the calculations are less than the equipments which are rated or available in the industry. So for the load flow and short circuit study, we will be considering these following 5 case studies or following 5 scenarios. In the first scenario, we will study the power flow in the microgrid with the diesel generators only. That means all other renewable sources are not available. In the second case, we will study the diesel generators along with the wind turbines. In the third case, we will study diesel generator, wind turbine, and wave energy generator. In the fourth case study, we will study diesel generator, wind turbine, and hydropower plant. And in the fifth case, we will study diesel generator, wind turbine, and electric vehicles. So this is the block diagram of the proposed system in this project. The diesel generators, the wind farms, and the hydrogen facility at the top is the existing system. In this, the hydrogen facility is currently not operational, and this indicates the 428 kilowatt load of Ramea Island. Our proposed system is indicated by the gray rectangle here. This is the wave energy generator, the pumped hydro system, as well as the combined vehicle to grid system. To carry out the load flow and short circuit studies in the project, ETAP software was used. The top figure indicates the single line diagram which was prepared in ETAP, and all individual components like the diesel generators, the wind turbines, the wave energy, pump hydro, electric vehicles, as well as loads were simulated and created in the model. So in this SLD, the gray rectangle indicates our proposed system, which is equivalent to this part of the block diagram. And the remaining system is the existing system on the left, and the load is indicated as this lump load below. So our first scenario is the case when only the diesel generator is running and all other renewable sources are not available. So this was simulated in ETAP by closing the breaker for the diesel generator. The standby diesel generators were open, and you can also see that the wind turbines were also kept open. When the load flow study was run, it can be seen that diesel generator is able to meet the active and reactive power of the load. 544 is the active power generated, and 337 is the reactive power generated by the diesel. And the results converged, and we can see that at the load we were able to maintain a healthy bus voltage of 99.98%. The required value is 95% or more. So the diesel generator can alone itself meet the complete load demand of the island of Ramea, even when none of the wind turbines or the new proposed system like hydro is not available. If we consider the same case for short circuit studies, we found that since diesel generator is the only source, about 1.444 kilo ampere, that is 1444 ampere of short circuit current is fed by the diesel generators into the bus, and the fault current as expected on the secondary side of the load transformer has increased because the voltage level is lesser at the load end. So this increases to 15 kilo ampere. However, these results are also within the expected parameters, because in industry we are able to get switch gears of 25 kilo ampere and more. So these results are also within the limit. So we can conclude that for scenario 1, both the load flow and short circuit studies were successful and within the expected parameters. If we talk about the second scenario is with the diesel generator and the wind turbine. So we close the breaker of diesel generators, and we also close the generators of the wind turbines. So The power flow started from the diesel generators as well as the wind turbines. Now the advantage of having renewable energy here was that the active power generation from the diesel generator has reduced to half. So now we'll consume less fuel, as well as the emissions from the diesel generator will be less, almost half of what was there when the diesel generator was operating alone. Uh, One more observation that we can have from this load flow study is that the reactive power generation from the diesel generator have increased. This is expected because wind turbines are induction generator, and for running they need reactive power. As a result, you can see the minus reactive power sign here, which is the reactive power consumed by the wind turbines and is generated by the diesel generator. But overall, the active power has reduced, and as a result, the fuel cost and the emission of diesel generator will reduce, and we will have renewable energy generation from the wind turbines. At the load end, we can see that the voltage is still within limits, much more within limits, higher than 95%. So we are able to achieve 99.98% of voltage on the buses. In the same scenario too, with the diesel generator and wind turbine, if we talk about short circuit current, now in addition to diesel generators, we also have wind turbines which will pump short circuit current into the buses in case the short circuit happens. So the total fault current has now increased to 1.973 kiloampere. On the secondary side, at the load end, this is around 17 kiloampere, which is less than 25 kiloampere. So this result is also within limits. The third scenario, which we were able to converge in this paper, was for diesel generator, wind turbine, and wave energy as the generation. So the breaker for the diesel, for the wind turbines, and this new wave energy generator has been switched on, and then the results were converged, and you can see that the generation of a diesel plant has reduced significantly as compared to the first two scenarios. Now the major part of the load is being fed by the wind turbines as well as the wave energy generators, and the reactive power required by the wind turbines as well as the load is shared by the diesel generator and the wave energy generator, because we will have a synchronous generator in the wave energy generation. In this case also, we are able to maintain a healthy voltage on the load bus, and the 102 kilowatt and 442 kilowatt active power is being met by majorly by the renewable generation in this scenario. For scenario 3, if we talk about short circuit levels, then you can see the three sources are now pumping fault current into the system. The total fault current is now increased to 2.089 kiloampere. Or on the secondary side at the load bus, this is increased to the maximum of 18 kiloampere. But still this is within limits of 25 kiloampere, so we were able to converge the results for the short circuit studies and keep them within the limits in the scenario 3 also. Scenario 4 consists of case similar to scenario 3. However, the wave energy generation has now been replaced by hydro energy. So you can see that the breaker for the wave energy has been opened and the breaker for pump hydro has been closed. So the total active power generation is now from the wind turbines as well as from the pump hydro. Active power from diesel generator has reduced significantly, and is the generator and the pump hydro are sharing the reactive power of requirement of the wind turbines and the load. The voltage is at the load bus is within the limits, and we were able to successfully get the results for load flow for this scenario also. For the short circuit levels, in this case, scenario 4, the fault addition to the bus by the pump hydro is 0.143 kiloamps, in addition to the wind turbines and the diesel generator. The total fault at the load bus is within the limits of 18 kiloampere or 18,086 amperes. Fifth scenario is the scenario where we show that a lump or a group of electric vehicles can also act as energy source. Such a system could provide stability to the microgrid in case there is a sudden load drop or load addition. Particularly in the load addition, these electric vehicles can provide rapid energy source for few minutes or even for few hours. So it increases the stability of the system. So we wanted to see how the load flow will respond when these electric vehicles cumulatively are connected to the grid. In this case, you can see that the active power generation from the diesel generator has been reduced to zero. The complete active power is being met by the wind turbines and the electric vehicles. The reactive power of the wind requirement of the wind turbines and the load is met by the diesel generator, because in this case diesel generator is the only prime source of reactive power. So in this case, we have to keep the diesel generator connected only for supplying the reactive power to the grid. This basically simulation basically shows the case that in case diesel generator is supplying in addition to the renewables, then EV can increase the stability of the system by providing a large amount of power surge for a short duration of time. In this case also, we were successfully able to maintain the voltage at the load bus. The short circuit values for case 5 are also within the limit of 25 kiloampere because of the slight addition to the fault level by the EVs. So if we come to the conclusion of these studies, load flow and short circuit, we see that renewable energy will result in reduction of the diesel generation output, and hence will result in the saving of the fuel as well as in reduction of the emissions. However, connecting such renewable sources with the microgrid will result in increase in the short circuit fault levels. As a result, there is a requirement to carry load flow and short circuit studies. In the first scenario, we indicated that if none of the renewable energy sources are available, then diesel generator is capable of supplying the entire load. In the second scenario, we indicated that the load on the DG sets can be almost half by using the wind turbines. However, we will need diesel generator to provide the reactive power. As a result, the reactive power in scenario 2 increases as compared to the first scenario. In the third scenario, we indicated that the load on DG set could be further reduced by having a wave energy generation in addition to the wind generation. Of course, now there are three generation sources, therefore the fault levels have increased, but they are within the limits. In the fourth scenario, the scenario is similar to third scenario, only with the fact that the wave energy generation is now being replaced by the hydro generation. The fifth scenario consists of DG sets being running in addition to the wind turbines, and electric vehicles of the batteries are supplying the energy demand in addition to the wind turbines. For the case we performed, we showed that the active power of DG set can be reduced to zero by using power generated from the wind turbines and the EVs. However, we will need the DG supply to provide the reactive power for the induction generators of the wind turbine and the load. One method of substituting the reactive power generation from DG set is to provide capacitors for supplying the reactive power for short duration. So in summary, we can say that all five scenarios for the load flow results converged. We were able to see the active and reactive power flows as desired from the model. In all the cases, we were able to maintain the voltage level within the 5% drop, that is more than 95%. In fact, we were able to achieve it at 99.98%. And also, the fault current levels achieved at various buses were within the limits of the equipment which is available in the market. And as a result, for with these fault level values, we can put up any system available in the market and commission it for the Ramea Islands.
Hi, my name is Lay, and I'll be discussing on frequency control of Ramea Island microgrid. So there are two primary methods of controlling frequency control. First is the group control, and second is the rotor inertia control. So due to the high impedance of a line, there are a high oscillation of power fluctuation when we control frequency. So the group control method will emphasize on controlling frequency as well as the power oscillation. So this is the system modeling we have used in MATLAB Simulink to check the frequency control in Ramea Island. So here the inverter is connected with the LC filter, and this is further connected with the load. Here we have taken the load set voltage and current to calculate the power calculation. Here these signals are in ABC reference and which are converted into the DQ reference to calculate the power, and the voltage signal are converted into phase lock loop system to support the power calculation in terms of frequency and the reference voltage of DQ. So now the active and reactive power of grid side is being compared with the reference active and reactive power, which are generated with the adaptive droop control. And the difference is the input signal for power PI controller, and the output of power PI controller is being sent to the current PI controller to supply the gate pulse of this inverter. So this is the basic MATLAB system modeling that we have used to create our MATLAB model. So now the simulation model of frequency control is being done in MATLAB Simulink, of course, and in MATLAB Simulink we have created two system models. One is for existing diesel and wind generation in Ramea Island, and the other system submodel is created to accommodate and to check the frequency control with increasing renewable energy sources with the Ramea Island microgrid. So with the droop control method, it is very important to set the droop set points for frequency and voltage. So for frequency, you have set the droop set point at 1%, and for voltage, we have set the droop set point at 4%. So here PI controller is implemented to generate DQ voltage reference signal for the three-phase PWM generator. So as shown in the figure, when the active power increases, frequency is reducing, and when active power decreases, frequency is getting increased. So these are two droop set point, F max and F minimum, set for our frequency regulation in MATLAB Simulink. So as we have set the frequency droop set point at 1%, frequency can deviate from 59.7 Hertz to 60.3 Hertz. And according to the inverter output characteristic, the output power also can vary to 10% of its rated power output. So this is the MATLAB Simulink model of existing diesel and wind generation facility with the proposed integration of renewable sources in Ramey Island. So as you can see, this block represents the existing energy system in Ramey Island, and this is the proposed renewable sources that we have already proposed, like pump hydro, vehicle to grid integration, and wave energy system. And these two sources we are connected with point of common coupling bus, and then it is connected with the load. So we have taken commercial load, residential load, and there is a variable load too with this PCC. So we'll simulate the effect of this variable load along with the droop control method. So here at 1 second we will increase the load, which is the variable load, and at the 3 second droop control will enable to check the frequency deviation, and at the 5 second of simulation time supervisory control will be enabled, of course, to check the frequency deviation. And this is the measurement block we have created in MATLAB to see the frequency change, active and reactive power change, and the voltage across the common coupling point. This is the submodel of our two-level inverter microgrid connected. So this two-level inverter is connected with LC filter, and which is also connected with the transformer, which is having voltage on primary side 480 voltage and on secondary side 600 volts. Here the control system is included to convert the ABC voltage reference to the DQ voltage reference, and along with that the output of PI controller generates the PWM reference signal to supply the gate pulse of this two-level converter. So this is the simulation result of frequency deviation when we have changed the load at 1 second. And as you can see from this figure, group control is enabled at 3 seconds. So frequency got dropped, and at 5 seconds there was supervisory controller activated, and system is trying to stabilize frequency again at 60 Hertz. So this simulation result shows the frequency is within the range of group set points, which are 60.3 Hertz and 59.7 Hertz. So this is the simulation result of voltage across the point of common coupling bus. So as you can see from this figure, the voltage across the PCC bus is 600 volt plus or minus 4% of droop set point that we have already set during simulation. And the voltage across this PCC is almost constant 600 volt as per our limit of voltage regulation for the frequency control and voltage regulation by droop control. So this is the simulation result of active and reactive power flow during the 8 second of simulation time. So as there was a load increase at 1 second, the active power increased from 1200 volt to 1600 volt. And during the 8 second of simulation time, we already checked the frequency and voltage are within the limit of deviation, and we have successfully regulated frequency and voltage with the increasing and dynamic changing of this load. To conclude the frequency control part of this project, we have simulated the frequency control effect with the Ramea Island existing energy generation system with the proposed energy generation system such as uh, pumped hydro, vehicle to grid integration, and wave energy with MATLAB simulating. And we can observe that the frequency control can be done with the droop control method, and the frequency deviation can be achieved with the 1% of droop set point. So simulation has done with the dynamic load condition as well, and frequency observed within the limit. So to concluding our presentation, for the first part of this project, we have done the E-type simulation with different 5 scenarios with the integration of renewable energy sources with current diesel generation and wind generation facility in Ramea Island. So active power supplied by DG sets get lower and lower based on the capacity added with DG set in terms of renewable energy, and the voltage drop across the bus is maintained with the minimum requirement of 5%, and the fault current level also within the limit. And in the second part of our project, we have simulated the results of frequency deviation with active group control method, and we observed that frequency regulation can be achieved within the 1% of limit with the increase of renewable sources such as pump hydro, V2G, with the current existing facilities in Ramea Island. And thank you for listening our presentation. And if you have any query or question, you can always reach out to this below email ID. Thank you so much and have a nice day.